Okay, so one thing that we talked about, and this was in the general playlist as well as some conversations that I have on my playlist about the turning a corner. Just a real quick refresher that, so when we turn a corner, when we're on the left lane, we're turning to the, we're making a left turn, right? The wheels are pushing, or the surface is pushing on the wheels to the left. And so that is a static friction force. Now, static friction, you have to kind of be careful, because when you just think of static friction as something not moving, and when you just think of kinetic friction as something not moving, it's easy to get confused. Static friction occurs when a surface is not, or when an object is not sliding relative to that direction on that object. And so, although the tire is moving forward, there might be a nominal friction force backwards. It's not moving left, excuse me, it's not moving perpendicular to the motion, obviously, and so that's the direction of static friction. We're not slipping perpendicular or otherwise. And so, yeah, we found an estimate for how fast we can take the corner without turning. By the way, I checked, we were going about 15 miles an hour when we took one of these left turns. We didn't feel very much. And that also underscores the idea of the model, because in this example of turning a corner, we are modeling the car as just a big 1,500 kilogram block of rubber that's in contact with the ground. And we are not considering the center of gravity. We're not considering the fact that the friction force and normal force might be different on different tires, compared with maybe driver's side versus passenger side, or with front tires from rear tires, or the fact that different number of passengers or the different loads in the car might affect that as well. I mean, these are all really what we in physics and science call higher order corrections to the first sort of problem that we deal with. And so, yeah, this is an opportunity just to underscore the point of simplifying assumptions. And yeah, we have to have simplifying assumptions, otherwise we're not going to be able to solve anything. So then we switch to banked curves, and the banked curves, we have the free body diagrams here actually. So in a banked curve, we don't need friction at all to traverse this curve, because the normal force is the thing that is providing the centripetal acceleration. Now, if you look at the free body diagram, you're going to see that, and they draw it relatively to scale, that the normal force is bigger than gravity, because the z component of the normal force, which points against gravity, has to be the thing that balances out the gravitational force. And I can even draw that really quickly. So going to this free body diagram right here, we have this vector n. Now, if I draw an arrow straight up, that's vector n sub z. That is the thing that equals gravity. So n sub c equals gravity. N sub z. N sub r now is the vector that provides the centripetal acceleration. The book doesn't define what a centripetal force is, precisely because of this reason that we might think that centripetal force is some new force, and you might categorize it with normal force and gravity, like normal force, tension, centripetal force, and that's not how we think about centripetal force. Centripetal force is always the result of a force, or perhaps a component, or perhaps multiple forces acting in that direction. So just keep that in mind. So yeah, the banked curves, and that gives us a precise, this equation right here, V, I guess they have the zero subscript right here, but V0 equals square root RG tangent theta. That is the speed with which we can take this curve without any use of friction. And something kind of fun to think about, if we quickly switch to the whiteboard, is those penny or coin kind of circle things that they have at museums and, you know, zoos and all this stuff where you can donate. It's always fun to watch it spin. So really quickly explaining that, yeah, so you got this is not what they look like, okay? But this is the basic case where you have a cone, a frictionless cone, and there's a penny spinning on the cone. Then, right, you have a specific radius and you have a specific velocity. If the cone is like this, where it's just the same angle everywhere, then what you would see here is this would not be a well-designed coin machine. Hopefully you know what I'm talking about. Like there's the things where you put your coin in right here, and you put your coin in like at the top right here, you slip it in, it's like slides down and gives it a lateral motion, and so this coin is just going down like that. So it's not designed like this, because what would happen is, if it was taking this curve, eventually the tiny bit of friction between, or air resistance between the penny and the air and the base here would cause it to slow down. And so when it slows down, that's going to make it go to a lower one. But without friction, this equation, this equation square root, RG tangent theta, means that as radius decreases, then the speed decreases. And eventually you get to the point where we're moving so slowly that you'll just topple over. So how do they get around this? The fact that if the thing was designed like this, then you wouldn't get the penny still moving. It would just eventually just topple over. You get around this by changing the angle. And so what they do is the angle itself increases. The angle of the banked curve increases the further down they go. Okay, so at first it's at a very high, very relatively shallow angle. What happens is, then as you get to the lower angle, or at the lower radius, you have a lower radius, but the angle, tangent of the angle, has gone up, and so it's still able to turn fast enough to where it's not going to eventually fall down. And near the bottom, it's very nearly vertical. The angle is very nearly 90 degrees. And so there's, at that point, it's pushing so far that it's actually static friction that's keeping it up. So those are always fun problems to consider. All right, so the idea then is that the banking angle increases as the radius decreases to accommodate for a fast enough speed so it doesn't fall over. Really, you don't really measure the speed on these examples. You actually measure what you see when it's spinning around is the rate of rotation. So omega would be V over R, right? And so omega would be, let's see, it'd be square root of G tangent theta over R. And if you look at this equation, by the way, where did we get square root RG tangent theta? That comes from just setting up the two equations and then solving them by canceling out the normal force when you sum for R and Z. But look what happens here. The omega, the rate of rotation, this isn't how many rotations per second, that's frequency, but it's related to frequency. As the angle increases and the radius decreases, both of those work together for omega to shoot up. And so that's why we see near the bottom, it's revolving maybe 10, 15 times per second. It's spinning really, really fast before it just plops down into the basin there. So it's a fun thing to consider. Let me move on though. Okay, and remark about friction. Now, I think if I didn't cancel out I just lost my mouse. Okay, so now this next free body diagram is if we take there it is, okay. The next free body diagram is if we take the surface at a speed less than the square root RG tangent theta. When we take it at less than square root RG tangent theta, then the surface has to accommodate by pushing upward. Because look at the relative sizes of these F nets, and they did a good job here to underscore that. So if we go to the previous slide, we see F net here. It's a nominal size. When you're taking it slower, F net has decreased. And so in fact, it decreases because now there's a static friction force that points up and to the right on the or laterally up the surface. So static friction is literally keeping us from sliding down the incline. Normal force then also has to decrease because now there's an upward component of static friction that's canceling gravity. So normal force cancels. So the normal force in the banked curve problem where you're going at less than the rated speed is less than taking it without friction at the actual rated speed. Now, for low enough angles, there is no minimum to how much you can take it. I mean, you can obviously see a stalled car parked on the highway of a banked curve just fine, and it's not a big deal. It turns out that the coefficient of static friction, like a chapter 6 problem, is that the coefficient of friction for a block, you can measure the coefficient of static friction by just taking the tangent of the angle, and I'm going to call this angle theta max, which that's the angle, theta max is the angle if you just keep this block at rest and you kind of lift up that platform. Theta max with respect to the horizontal is the angle at which it starts to slip. And you can show that tangent of theta is the measurement for the coefficient of friction. So what is it for rubber on concrete? Well, the coefficient is 1. Right. For rubber on concrete, the coefficient of static friction is 1.00, which is going to make theta max 45 degrees. Right. The inverse tangent of 1 is, it's the angle at which the sides are the same. So 45 degrees is the angle. And so anything less than 45 degrees, then even if you were at rest, then the car or the object on the bank curve still wouldn't slip down. And that's when the normal force is actually at its lowest. It's actually equal to mg cosine theta when it's at its lowest, when it's not moving. And then when you are moving, the normal force does increase. The normal force does increase. But there's no limit to how slow you can take this banked curve. Compare that with the next case of taking the banked curve too quickly. When you take the banked curve too quickly, now we have a situation where the street or the surface has to push down on you to keep you from skidding up. And the normal force gets larger still. And there is a maximum speed in this case. And there's a homework problem in which you'll explore this, but there is a maximum speed at which you can take this curve without skidding upward, because the faster and faster you take this curve, this normal force will get bigger and bigger. This static friction force will get bigger and bigger. But of course, what we know from static friction is that there's a limit to how much the surface can push based on that coefficient. And so this is a really good, at a specific angle that is less than, I guess, the inverse tangent of mu. If the angle is less than that, which again, for banked curves on highways, you're not going at 45 miles an hour, or you're not going at 45 degrees. For angles less, then yeah, there will be a maximum. You can find an expression for V max because the F net will keep increasing. So you do that in a homework problem. One final interesting remark about these banked curves is that if you switch the situation, what about, so 45 degrees is kind of a strange angle to work with. But what if you take a banked curve, and this would be like not anything on a highway, but something more like, I want to say daredevilly, but if you take an angle bigger than that specific angle. Well, now in this case, in order to take this curve, right, that's banked at a very large angle, 60 is greater than, well, it's greater than 45 degrees, obviously, but the important thing is that if you're taking it at an angle that's greater than inverse tangent of mu s, then the roles switch. There is no maximum speed with which you need to take this. And that's interesting, is that there's no maximum speed with which, well, yeah, there's no maximum speed with which you can take it, because friction and normal can just keep increasing. But there is a minimum speed, right? Because obviously if we had this block at rest, it's just going to slide down. And so it's this torturous scenario where you have to maintain a minimum speed before you slide down, and there is no maximum speed. And the case in point is, think about that penny as it's falling down in that little coin table thing. As it's falling down, I mean, it's spinning nearly vertically on near the bottom, and so there's no maximum speed to how fast you can take that. It would just make the normal force even bigger. So that's kind of interesting thing to flip around about banked curves. Anyway, so briefly mention that. Let's see, so we have a quick check question here. Let's take a look at what are these free body diagrams. The next topic is on centrifugal force, which is an example of what we sometimes call a fictitious force, or sometimes we call it an inertial force. These are sensations that we feel as a result of us in a system that's accelerating. What do I mean by that? Well, the classic example is the car turning a corner. It doesn't even have to be a banked curve, but a car turning a corner, right? A bird's eye view, watching this car turn that corner, we know that there is a acceleration. Oh, this is a banked curve. There's some force pushing it towards the center of this circle. And yet we feel that we're pushed to the right. We're pushed in the direction that's actually opposite of our actual acceleration. And that's just how the world works. So the centrifugal force, I feel like some places I've heard it called centrifugal force, like centra and then FICAL. I feel like that's shown up, which causes even more confusion, because the centrifugal and centrifugal forces are meant to be the same idea about the sensation of being pushed back. The classic example that perhaps you may have experienced is one of these tilt-a-whirl rides at an old amusement park. So in this picture, you have, in this picture, you have this ride right here, this like cylinder. And what do? You stand on the sides of the cylinder, and the cylinder rotates, right? So a person on the right edge here, person on the right edge here, okay, they're stuck to the side, right? Okay. What's the free body diagram they're going to feel? You have R-axis that way, Z-axis that way. So in this case, they'll probably feel like mg down, and then a normal force from the floor up. This isn't very neat, but normal force from the floor. But now you have a normal force from the edge, or normal force from the wall. And the normal force from the wall is the thing that is moving you in a circle. So what do you feel when you try and lift yourself up? Because you really do feel pushed against the wall. That's why there is a normal force there. But what do you feel when you try and peel yourself off the wall, and you always try and walk towards the center? They put this little chain here, right? That's not gonna protect anybody, but that little chain there is meant to keep us in our spot. But what would happen if we were to walk off of the wall and towards the center? And so as we're watching this, we're watching the thing rotate. And so we, in our Newtonian frame of reference, is watching this thing rotate, and we're saying to ourselves, the person is accelerating towards the center. And so the normal force on the wall is equal to the net force. And we would sound like we really know what we're talking about, because, the net force equals the normal force. But that's not true of what the person on the thing observes. Okay, this is what we call an inertial reference frame, where we have our kind of our XY axis kind of on the ground below it, and we're just watching it rotate. But what about the people on the amusement tilt-a-whirl thing? I don't think it's called that. It used to be called the Bamboozler at Worlds of Fun. I don't know if it's still called that though. But what about the people on the thing? They're not accelerating, or they don't observe themselves moving relative to the apparatus or the ride. Let's just call it the ride. They don't see themselves moving relative to the ride. And yet, if you were to put a roof on here, and you were to, there weren't any windows or anything, and the people were just spinning there, they would observe that they are not moving. And so they would have an F net, which would equal 0. Because they're not moving relative to the spinny thing, and yet they feel like they're shoved against the wall. And so what is their free body diagram going to look like? The person on this side, they're going to have, I'll draw it down here, I guess. They'll feel the same gravity. They'll feel the same normal force of the floor. They'll feel the same normal force of the wall. But since they are not accelerating relative to the spinning ride, they have to now conclude that there is a force backwards. And the book would call this the centrifugal force. I think more generally, I would just call it a fictitious force. And it is a fictitious force because this is just a result of our inertia. The fact that we're really being pushed along by this surface, when really we just want to stay in a straight line path, because this person right here, they want to just fly off in that direction. And so the centrifugal force, or what we call the fictitious force, has to push us to keep us moving in a circle, the normal force rather. So this is an example, and of course, when you turn a corner, if you turn to the left, you feel flung to the right. Well, what's the agent that's flinging you to the right? Nothing. There's no external agent flinging you to the right. This is just a result of your inertia. Now, again, the book calls it centrifugal force, but if we return to some other examples, we can see that the centrifugal force is really just another one example of all of these quote unquote inertial forces. So if we look at, these drawings aren't that great, but if we look at like a truck, or someone in a car that's slowing down on the road, right? We got the bed, we got the pickup, we got the cab, okay. It's not that great. So let's say the person on the side of the road, right? on the road with the coordinate system attached to the ground. If they're moving forward, and when they slow down, they're accelerating backwards. Okay, what do we observe? We observe that, there's the normal and there's the gravity. And there's a backwards, if their tires are skidding, there's a backwards kinetic friction force, which is the resulting F net. Okay, so this is the inertial system. This is what we're measuring in a coordinate system that is either at rest or moving at constant velocity. What do people in the truck observe? And this kind of goes back to the relative motion stuff we talked about a little bit in chapter 4. So it's related, but so what do people on the truck see? A coordinate system on the truck. Well, the person in the truck is not accelerating relative to the truck, or the person in the car is not accelerating relative to the car. And so they're going to say that the F net is 0. They observe that there's an mg, they observe that there's an n, they also observe a friction force. But in order to maintain a 0 net force, because the person in the truck is not moving relative to the truck, they have to once again invent a forward fictitious force. And this fictitious force equals the friction force. And so hopefully you're starting to see the pattern that in the inertial frame, what the inertial frame observes as F net, the non-inertial frame observes as a fictitious force in the opposite direction. And this is something that I've been harping on for a while, saying that when you yourself are accelerating, you feel a fictitious force in the exact opposite direction of your accelerating. Okay, anyone who ever takes like the shuttle, or if you've been standing on a bus when it's moving, knows that you feel all these pulls to the front, to the right, and you're always accelerating in the exact opposite direction in which you feel you're being pushed or pulled. There's nothing that's pushing or pulling you. In fact, the thing that when you turn left, you're being pushed to the right by the surface, and you're being pushed to the right really by the friction in point of contact of your like feet or your seat with the ground. Okay, so inertial forces come in more than just centrifugal forces. So that's why I'm being a little bit more general. This is a classic example. I mean, also the elevator, moving, accelerating up or down in an elevator is another example of those extra forces that you feel, where the normal force is different, but we would invent a fictitious force because we're not accelerating in the elevator. For what it's worth, that there is one more example of a fictitious force that is not in the textbook, but I think it's worth mentioning at least once. I think you'll see it in dynamics. And I would argue that this chapter isn't nearly as good a preparation as it should be for those later classes you'll be taking. But there's one final force to talk about. And let's go to the merry-go-round. So again, this conversation is not in the textbook, and nor will you be expected to do homework on it. But let's say you're right here. Okay, you're standing right here. And there's enough friction to where you're stationed. So if you're at rest relative to the rotating merry-go-round, in this direction, you're going to feel a backwards fictitious force. But what's going on is you feel a static friction force towards the center. So you feel a static friction force towards the center and a centrifugal force, let's call it maybe F sub CF, centrifugal force, right? Because standing on the rotating platform. Now here's a question. What happens if you try to move on the rotating platform? This is great. What happens if you try to move on the rotating platform? Let's say you move away from it. I should draw a bigger picture. Oops, no, undo too far. Or undid too far. Okay, so if you're moving away, so if you're on the rotating platform and moving away from it, think about this for a second. What would happen if you were on the merry-go-round and there wasn't any friction? This is neat. And the best way to maybe describe it would be to draw some spokes on this merry-go-round. Again, this is a bird's eye view of the merry-go-round. So maybe that, and then like dotted lines or whatever, okay? What would happen if there was no friction is as you walked outward, the merry-go-round would rotate, right? And so that would be like there, that would be right there, and this would be right there, but you'd be in the same spot on the relative to the ground, right? Does that make sense? If there was no friction on this merry-go-round, besides feeling an outward pull, no, you wouldn't even be feeling an outward pull at all, because there'd be no friction. Okay, you'd just be, again, if there's no friction, just imagine a slick surface just rotating past you, and there's no friction, and you're standing exactly where you're at, relative to the ground, but the surface just sliding past you. So as the platform rotates, it rotates in that direction, and if you're moving that way, you don't feel anything. So the point of this is that if you are moving and there is friction, you actually feel a force perpendicular to your motion. Does anyone want to take a guess as to what the name of that force is? This is actually called the Coriolis force. And again, this is not a real force. This is the fact that the Coriolis force only, sometimes it does that. The Coriolis force only comes into play when an object is moving relative to something that's rotating. So, and it's always perpendicular to the direction of motion, right? Because think about what's got to happen in order for us to move outward in a straight line is that the friction on the wheel needs to be pushing, or the friction on the platform needs to be pushing us forward. Otherwise, we'll slip to the other spoke, or not spoke, but other section of the wheel. And so the surface needs to be pushing us to keep us in that direction. If we're moving the opposite way, then if we're moving the opposite way, then it's the same effect actually, that the surface needs to keep us on the specific ray or spoke that we're actually at. So that's the Coriolis force, and we're not going to talk in any detail about how to quantify that, but the direction is it's always perpendicular to your motion. That's why sinks and tubs and toilets and all these other things, they drain in the northern hemisphere, they drain clockwise. They drain clockwise, and in the southern hemisphere, they drain counterclockwise. And there's been, interesting videos on YouTube where two, scientists on either ends of the earth perform the same experiment. And one rotates clockwise, the other rotates counterclockwise. And there's all sorts of other interesting examples of the Coriolis effect. Rotation is another big spot. I mean, that's why when you talk about hurricanes, those that form, hurricanes that hit the Atlantic generally form kind of off the coast of Africa. And that motion that they have moving on a rotating Earth will give it a clockwise motion in the northern and a counterclockwise in the southern hemispheres. So certainly not something that we're expected to know for homework or for the test, but I think you talk about that quantitatively in a later class for engineering majors. Let's talk about two more examples involving vertical circles. We got a couple minutes left, so let's start with the going down a platform problem. Okay, how does the normal force change? How does the normal force change when you get down into a valley? Okay, the sensation is that you feel shoved into your seat, more or less, and your speed, on your own, your speed would probably increase, but we're just comparing the same speeds. How do the normal forces compare in these examples? We have, for the thing at the top, we have normal force equals mg. Now at the bottom of the circle, we're accelerating upward. And so we have F net upward, which means normal force has to be bigger than mg. So that's kind of interesting. And that is the feeling that we get when we go down a hill. I would, consider like examples of roller coasters when you take a high curve and then you're falling down and then you instantly shoot back up. You literally feel shoved into your seat, like someone is like taking your shoulders and literally pushing it down, pushing your shoulders down, crunching your shoulders down into the, your body, which then crushes down into the cushion of the seat. And that is the same thing in this case, because we're accelerating upward. Because once again, you're at the bottom of that valley, you are accelerating. And so what you feel is pushed down because you're accelerating up. So just another instance of a fictitious sort of addition to the normal force. What about going over the loop? Or what about going in the loop? Okay, what about now at the top here? If you're taking the top of the inside of this loop, then once again, your F net points down. So normal and gravity point in the same direction now. So we have normal force down and mg down. And those add to F net. So those would sum as n plus mg equals F net, which again for circular motion is just mv squared over r. But notice here, gravity is obviously constant, but normal force is not. Normal force will change based on the speed. And so you can say that the sensation that you feel, how much your seat is crushed into the chair, is proportional to the speed, squared rather, at a constant radius. And so you can take this, the faster you take this turn, the larger the normal force is. But the slower you take the turn, the smaller the normal force is. But you can imagine there's a limit to how slow you can take the turn when normal force becomes zero. Normal force never flips direction. Surfaces don't have hooks. They're not going to grab onto you. And again, this is like more like a Hot Wheels track, not like a roller coaster with all the safety stuff. But yeah, at that point, you would have mg equal to mv squared over r, and you'd get the equation v equals square root r g. And so that represents the minimum speed with which you can take the top of the curve without becoming a projectile, because any less than that speed at the top of that curve with the given radius, your trajectory is now parabolic, not circular. That is, you're in free fall and you're falling off. So normal force can be any value in this example, but it can't, once it's zero, then the speed cannot be any value. The speed has to be greater than RG. And then once you have that, then the normal force increases as the speed increases. Anything less than square root of RG, you're falling off of the inside of the curve. So that's the loop-the-loop. There's one more example over the hill, which I think we'll mention briefly next time.